Here we're given a problem and asked to figure out the dimensions of a box. It says here, airline regulations, we all know that they have some specific requirements for the types of carry-on luggage we can bring on. So it says, suppose that we have an airline policy that states that all baggage must be box-shaped with a sum of length, width, and height not to exceed 64 inches. So what are the dimensions and the volume of a square-based box with the greatest volume under these conditions? So in that very last sentence, it said the greatest volume. So right away, we know that we are going to maximize volume. So maximize volume. And volume for this figure over here, so we are given the image already. When we think about volume, volume for this particular equation or for this particular shape would be the area of the base times the height, or in other words, W squared times H. So W squared times H. Remember, this equation that we just found, the one that we want to maximize, becomes the primary equation. Now we have to come up with some sort of secondary equation because, again, volume is written in terms of two variables here. So I have to have another equation so that I can make the substitution and rewrite volume in terms of only a single variable. So what is that second equation going to come from? Well, if we look back to our question here, it says that all baggage must be box-shaped with a sum of length, width, and height not exceeding 64. So the sum of the length, the width, and the height must not be greater than 64. So if we have the length, the width, and the height, and we add them together because that's what sum is, so I would have 2W plus H cannot be greater than 64, this becomes our secondary equation. That's our secondary equation. And I can rewrite this secondary equation in terms of a single variable to be able to substitute back into my volume or primary equation. Now, again, I can solve this equation for either W or H, but because H has a coefficient of 1 in front of it, it is actually the easier variable to solve for. So I would have H is equal to 64 minus 2W. From here, we're going to make our substitution into the volume. So the first thing that we did is create our primary and our secondary equations. Now we're going to rewrite the primary equation, volume, in terms of a single variable, W. So I have W squared times H, but we are representing H with 64 minus 2W. Simplifying this, we have volume is equal to 64W squared minus 2W cubed. So I have my volume equation, and I now want to come in and I want to take the derivative because it's this equation we're trying to maximize. So we take the derivative of our primary equation. So V prime is equal to 2 is going to come down, so I have 128W minus 6W squared, and it's this derivative equation that we set equal to 0 because we're finding the maximum. We got to find the critical values, so I will solve this equation here. From this, I'm going to factor out a 2W. So 2W leaves me with 64 minus 3W equals to 0. We can see that 2w equals 0 or w is equal to 0 for that factor. For the second factor, we would have 64 is equal to 3w, or w is equal to 64 thirds. Now, it would be a good time to point out that W is the width that we're looking at. So for me to have a critical value of 0 here doesn't exactly make sense. So I don't need that W, because remember, we're looking for the maximum value in the first place. So instead, we have this critical value here, right? This is our second critical value from our equation, and it is the max that we are looking for. So we're going to test and make sure, is that indeed a max? So we would do that again by taking the critical value of 64 over 3 and evaluating the derivative v prime to the left and to the right of 64 thirds. When we do that, we find out to the left it's positive, to the right it's negative. So we would be increasing on the left, decreasing on the right, and therefore by the first derivative test, we are able to kind of identify that yes, this 64 thirds is indeed a maximum value. So what do we do with that? Remember, the question here says, what are the dimensions that are going to give me a maximum volume? So we're looking for both dimensions as well as the total volume. So that's the third thing that we want to identify here in this problem. So the dimensions, we already know what W is, but we can use our equation from back up here at the top that said H was equal to 64 minus 2W to determine what the height of our box is supposed to be. So we would take that 64 minus 2 times 64 thirds. And when we plug that into a calculator or we do some math here, we're going to find out that 64 minus this fraction here ends up being actually 64 thirds. So what that tells me is that we would have a width of 64 thirds here and here, because we said it's the same, but we also know now that the height is 64 thirds. In other words, we would have a cube, wouldn't we? So we would have a cube for our maximum dimensions, and then the volume representing that cube is going to end up being 64 thirds raised to the third power, and that ends up being 9,709 cubic inches. So for this particular problem here, again, we had to figure out what the primary equation was. It had to do with volume. We had to come up with a secondary equation from the problem that was given to us. So this is where we had the 2w plus h equals 64. We're able to solve that secondary equation so that we can then rewrite volume in terms of a single variable. Once we've done that, we take the derivative to be able to find the critical values and then test to make sure that that critical value is indeed a max.